complete day when I get somebody to go, ugh. Okay. You guys all right? Anything else before we get into new stuff? Even if there was, that's plenty. Here we go. This isn't even really... Did I turn that on? Yeah. Old man Jeff. Oh, it's going. Young man Spencer. I've kind of been getting you ready for this next chapter. What did I say about this next chapter? Anybody remember? Little. Huh? No, we've already seen that. What did we just learn? What was the whole last chapter about? Factoring. So what did I say about this next chapter? It all will involve factoring at some point. Right? I say that because if you are not good at some forms of factoring, you gotta focus on that shit first, because you're not gonna be able to do anything in chapter 7 without knowing how to factor. Huh?
It's basically like a ton of factoring.
Yes.
Okay.
Yeah. So it's like we learn how to factor, and then chapter 7 comes at us with the most immediate uses of it. Right? So we already know one use is to solve equations with higher degrees. Right? So we already got one very useful application. So, and then I kind of gave you guys a preview of this type of dude. What do you got, Jeff? Yeah, sure. What else you got? Show me what you got. Okay, there you go. The old man in the seat. Are you watching Rick and Morty?
New episodes in a few weeks.
Dude, no, yeah. No, it's already here, dude. All right. So we talked about this before. Can somebody please tell me why I can't just start, 9 and 27? Don't they reduce? Come on. Don't they reduce? And then the x squared and the x cubed, I can reduce those, right? Of course not. Can't. Why? They're not multiplied.
Yeah.
The reason I could, if I just had 9 over 27 all day long, I could reduce the shit out of that. Because what's division the opposite of? And 9 is 3 times 3, and 27 is 3 times 9. I can even make it better. Just freaking 9 is 1 times 9, right? Wow! And because division will kill parts of a multiplication. Division can't touch parts of a subtraction. It's not designed to do anything with that. So, but what can I do at the top? Yeah. What form is that?
X plus 3.
Yeah, it's in difference of squares. X plus 3.
Minus 3.
X minus 3. And what about the bottom? Cubes. Little dude, big dude. All right, let me stop for a second, you guys. So this, what's up? Everybody all right?
Yeah.
We normally don't do this step, do we? Because we have a much better handle on numbers. We've been working with numbers a lot longer than we've been working with variable expressions. So I normally don't even see this step, but I like to show you this is really what's happening. Since I can break it down with multiplication, division can do its job. So that's exactly what I think with this kind of problem. The instructions would either say simplify or reduce, and that's exactly what we're trying to do. We're trying to reduce the same way we did here. So the bottom is the cubes. So this is basically just 2 factoring problems thrown together with one extra step. So how do I do this? What goes in the little dude here?
X. Yep, X minus.
Yeah, x minus 3. So then
X cubed.
X
squared. Yeah.
Squared. Over here would be
9.
9. And the sign here is plus 3x.
Yeah, 3.
Become a 3. So then what dies? Yeah, same way that the 9s kill each other, this dies with this. And so I get this. Shabbat.
So it's literally just finding out what cancels out to get to that.
It's the same thing we do here. It's just we're not used to seeing this. So our brain kind of goes to what we know and tries to kill the 9 and the 27. But you got to stop it. You got to say, oh, shit, there's subtraction there. I can't kill it. Division isn't that strong. It can't kill parts of a subtraction problem. Yes?
How do you know to do x minus 3 as the first portion instead of putting the bigger portion in the big part.
Because what goes here always is same sign. Same sign, opposite sign, always positive. These apply soap. Okay, I like it. Maybe. And let's see. Let me do. I haven't done this in a while. What if x is 4? Well, this might be. Well, we'll see. What's going to happen here, Jeff? Let's make x 5. Just because. What do I get here? 25 minus 9. 16. Is everybody with me? What's happening? Why did I pick 5? Well, can anybody tell me what I can't pick? If you look over there, you should be able to see what I cannot pick. What value of x? X can't be 3 because that makes the bottom 0. So I'm going to pick 5. Right? You could have picked 11. So 5 squared 25 minus 9 is 16. 5 cubed is 125 minus 27. Well, 125 minus 25 is 100. Minus a couple more is 98. Right?
Yeah.
Okay, I like it. Can this reduce? Yes. Well, let's see. What would this be if x is 5? 5 plus 3? 8. 5 squared, 25, plus 3 times 5, 15, plus 9. That's 8 over 49. And what do you get when you reduce this? 8 over frickin' 49, right? So on one level, I really appreciate it when you guys go, oh, wow, holy shit. On the other level, of course, because what did we just do to this? We reduced it. So if I put a value of x in, it will reduce it. When I noticed about 4, the reason I didn't use 4 was 4 would have been 7 over, you could do it. Can you do it, Jeff? I think 37. And can you even reduce that? That would have been kind of boring. That's 7 over 37. If I put a 4 in here, that's 7 over 37. Ew. So this was a little more interesting. Right? You guys semi with me? Do you have to do what I did in green ever? No.
No.
But it is the concrete part of this abstract business we're doing up here. No matter what value of x is, this would be a way to reduce this. Okay. What about this question? I gave you this question before also. What's that, LP? What's the domain of this? What you got, Jeff? There we go. No, that's not good. Try again. Yeah, sure we go. And look, just as a reminder, here's an easier question. What's the domain of this? And let me ask it a different way. Let me say, what can you not use for x? 2. So what's the domain? Everything except 2. So remember, what's domain mean? It's a collection of all the x values that I'm allowed to use. So very often an easier way to do it is go, well, what can't I use? And the answer is everything else. So what values of x can I not use here? I don't know yet. What do I want? How did you guys figure out it was 2? Because what did you make the bottom equal to figure that out? Because that's where things would go wrong. So how do you figure this one out? You set the bottom equal to 0. And of course now we know how to do that. I have to do what with this? And of course, did I make something that doesn't work? Shh, why not? Of course I did. Make that a stupid 6 there. I don't care. I'm tired. Right? And now that I made that a 6, will this work? Yes. Minus 10 plus 4. So x. Let me show you now. Watch this. One little difference here. Are you guys cool with this? Right? What can't happen? The bottom can't equal 0. So this can't equal 0. So x can't be 10, and x can't be negative 4. Kabam. Maybe. So this is old news. We've done this problem before. This is a little bit new, but once I break it up, it looks like two of these kind of problems. Bam, bam. Yes. Yes.
So the question is, numbers make the denominator 0.
Yes.
Undefined. So we
What
can-
numbers make at the bottom? 0, because that makes the whole thing undefined.
So we can put like this.
Beautiful. So if I said, what's the domain of this guy? X can't be 3. And I really want you guys to realize this. I am not allowed to kill these for one value of X, if X was 3. Because tell me, what is 0 divided by 0? No.
Undefined.
What's anything divided by 0? Infinite or undefined. What's 0 divided by anything? 0. So what's 0 divided by 0? Undefined and 0 at the same time. Right? It's the same thing as what's 0 to any power? 0. What's something to a 0 power? 1. So what's 0 to the 0? Somehow both 0 and 1 at the same time. So these are two things, examples of what's called indeterminate. It's like undefined to the next level.
That's pretty funny that 0 to the 0 power is 1.
No, it isn't. It's not what you just said.
No, you say
Anything to the 0 power is 1.
Okay.
0 to any power is 0. Is that
Oh, yeah,
right?
yeah.
So 0 to the 0 has to be both 0 and 1 at the same time somehow.
Sorry, kind of.
I'm sorry. I don't mean to. I don't actually. It's not that I don't care, but this is the reality. So I'm going to tell it to you kids. Tell it to you straight. And it's really kind of nifty. You don't even get to analyze this kind of thing until calculus. Some of you guys are like, I'm fine with not analyzing that further than the shit you've said already, Jeff. Damn.
So 0 to the 0 power is what?
Indeterminate.
Indeterminate. Okay.
And so is 0 over 0. It's indeterminate. So if you Google that, have fun. Okay. It involves something called limits, and we're not gonna. That's calculus. So what was my point with that? Oh. So the only time I can actually do this is if X isn't 3. So the minute I write this down mathematically, I am telling everybody that X isn't 3. Because if X could be 3, this expression is meaningless. So the minute I write this down, I'm actually saying X can't be 3. And then I can do this legally. Because then it's not 0 over 0. Do you guys see that? So if I said, what's the domain of this? That was very Christmassy, I didn't even realize. What's the domain of this? Don't kill that and say the domain is just not -2. X can't be 2 or -2. Then I could kill this as long as I know this. I like it. What's really, really neat is if I graph this, I know that's way in our view, but if we graph this, there's going to be a hole or a wall here and here. Because X is not allowed to be these things. So when the graph kind of comes across 2, here's 2, there's going to be a hole there. Because it's not allowed to equal 2. Right. And then, I don't know if I wore for you guys my Lord of the Rings shirt that's like, you shall not pass. Did I ever wear that thing for you guys? It's got an asymptote, no? What? I did wear that once to a final exam and somebody took it personal. I'm like, well, I think you probably should. But anyway. So it has nothing to do with passing or failing class. It's just, there's like, it looks like this. So here's a wall, right? So this is what would happen if I had like 1 over x minus 2. All right, we're kind of, I'm just going to finish this discussion up and then we'll head out. Stay with me. Who's got a calculator right there next to them somewhere? Anybody? Well, let's do it real easy. What happens at 2? on the bottom. So officially this is undefined. So how do I analyze this thing at 2? Well, if there's something like looking weird, what do? Get closer to it. You don't go right up on it like the guy in the movie The Blob. He actually touched the damn thing. I'm like, why? Get close to go, that's weird as shit. I'm going this way. You know, instead of like, what is it? Whoa, shit. If I get really, now watch, this is kind of cool. How do I get close to 2? Because I can't put 2 in, can I?
No.
But I can put every other damn number in there. So why don't I try 2.1?
Yeah.
That's really close. I'm like, what is that thing? So if I put 2.1 in there, let me show you how you don't need a calculator for this. 1 divided by 0.1 is 10 divided by 1. So I get 10. So you can double check me. 1 divided by 0.1, you get 10.
Yeah.
Now we can get even closer. What if I get to... So my picture's wrong for this guy. What have I done here? Sorry. It's like this. Oh yeah, I made that up after I made the picture. That's right. So at 2.1, it's at 10. You guys see it? I would have the point at 2.1. The output's 10.
2 point.
Now what if I try 2.01?
100.
That's 1 over 0.01. That'll be 100. So at 2.01, it's at freaking 100.
You can keep going on like that.
So that's the idea of an asymptote, is I just keep getting closer and closer and never get there. And this is how you investigate stuff like this or stuff like this, is you get closer and closer to 0 and see what it's doing. Anyway, that's more than we have to worry about here. Sorry. I just couldn't stop myself.
You get that like very far from
Yeah, it's way in our future. But since we're starting to talk about what are called rational expressions, because they are a ratio of expressions, so we call them rational expressions, because again, we're very creative people. This kind of thing will come up. So, all right. That's enough for today.
I have a question.
Yeah.
So for infinity, you can, like, what is it? I remember watching a video about infinity and it explained it used a hotel.
Yeah. If you have an infinite number of rooms, you get one more, and it's all full.
Yeah.
And one more person comes.
Yeah.
All you have to do is move people over,
Yeah.
and now there's enough rooms again.
Yeah.
Yeah.
I get it, but the thing is, it's just like